You'll have so many credits.
Yeah. Now that I think about it, I have a lot of credits.
You have a lot of credits. I have like 500. You have awards. Did you attend any English classes?
No, not really, because I covered my I had the chance on the
Alright, hello everyone. We're going to get started now. Today's recitation, we're going to talk about some basically just concepts that you'll need to have to understand logistic regression, which is coming up. So all of the things that we're going to talk about, there are many more things associated with each of these subtopics, but we're only going to focus on the pieces that you're going to need to know for the topic of logistic regression, which is coming up. So these different areas we're going to talk about, first linear algebra, but mostly we just want to make sure that you understand the concept of taking a derivative, especially with respect to a vector. Then convexity, so we'll go over what is a convex function, why convexity is important, and how you can determine if the function is convex. And then for optimization, the only technique we're going to talk about is gradient descent, which relies on you knowing how to take gradients and a function being convex. So everything comes together. Then if we have time, at the end we'll go through an example of taking a maximum a posteriori estimate. So to start off, so linear algebra, but mostly just differentiating. So does anyone want to just shout out the derivative of this univariate function, 1/2 x squared? Yes. So that was nice and easy. Now, what about the gradient of this function where x is an n-dimensional vector? Yeah, it's still x. So there is more hesitation about that one. So maybe, ideally you have already learned this at some point, so you're just a little rusty on it. But even if this is the first time you've heard it, we'll go over it now, and you can still do everything. You just might have to build up your background on this particular thing. But yes, it is still x. So if you have a function that is takes a vector as input, so we'll denote that as you're going from an n-dimensional vector of reals to a single real number as your output. The higher dimensional analog is sometimes called the gradient, and that's also going to be an n-dimensional vector. And you can think about just computing it element-wise. So x here is an n-dimensional vector, so for each, when you take the gradient, each component of the gradient is when you differentiate your function with respect to that single element. So do you know the concept of like taking a partial derivative? Okay, I see a thumbs up and some nods, so that's awesome. So now we'll do the example from the previous slide, but looking at doing it element-wise. So I'll just write this on the board. Here our function is 1/2 x transpose x. Does everyone understand this notation here? Just raise your hand if you understand it. Okay. Oh, okay. Everyone raised their hand. I was going to be like, maybe someone's just too lazy. So if you were to write this out element-wise, you're going to have this 1/2 in front of everything. But here, right, if you have, we'll say that this is x transpose, and this is x, they're both n-dimensional, so you have x1 through xn, x1 through xn. So here, this x transpose x, you just multiply x1 here by x1 there, so you get x1 squared plus, and then same through x2, all the way through xn squared. So now, if we were going to go and look at this component-wise definition of the gradient, you would know that your first element in it is going to be differentiate this function with respect to x1. Well, the only time x1 appears is right here. So it's just like the first thing. So it would just be x1, and then similarly for all of your x's in there. And that's how you can see that it comes out just to be x for your gradient there. So most of the identities that you know from single variable calculus have higher dimensional analogs. And there are a whole bunch of different things, like you can take a vector with respect to a matrix, with respect to a scalar, but here we're focusing on vectors. So here are just a few that are going to be important. So on the left, just an example of a function, and then on the right, we're going to have the gradient of that function. So if you have b, which is a real number that has absolutely nothing to do with x, you probably already know what the gradient is with respect to x. 0, yes. Now, what about a? A is also an n-dimensional vector. A transpose x. Right, A. And then this example we just went through, it's x. And here, if you have a composition of functions, just like you have in single variable calculus, you get the chain rule. So you first take the derivative of the outer function with respect to its argument, and then you multiply it by the derivative of your inner function by what your variable x. And you can extend that to any number of chained functions nested within each other, just like you do in single variable calculus. So there are many more identities and resources that you can use to look at them. One popular thing is called the matrix cookbook, and then also just the Wikipedia page on matrix calculus has a ton of tables with these various identities and more. So now that we have these identities, let's go through another example where you won't need to hopefully go through things element-wise to compute, because that can be time-consuming and rife with errors because you have so many opportunities to make mistakes. So here, I'll give you a couple minutes, and just look, we have this function h, and then I'll give you some time that you can solve it on your own, and then maybe someone can come up to the board and do it, or we can do it together. All right, it looks like most people have stopped writing. Who has an answer? So everyone just gave up. Is that, or just, this doesn't mean you're volunteering. There will be a separate call for volunteers. Okay. Like 3 people. Oh, okay, more people. So those of you who didn't raise your hand, if you had more time, could you get at it? Like, do you want another minute? Or are you confused and just want to do it and see how it's done? All right, in the interest of time, call for volunteers. Yeah, okay, you can either, yeah, just come up and do it. Oh, I meant to give you all the... Sorry. Right. Oh, yeah, you can go ahead and explain it.
Basically, just chain rule, bring down the exponent, which is 2, and then you decrease the exponent by 1, and then you multiply it by 3.
That's right. Also, what's your name?
Akshay.
Akshay, okay. Cool. Yeah, so here you can notice that this is a composition where your inner function is basically what's squared, and then your outer function is just squaring a scalar, and then apply the chain rule here. So that is all we will. Oh, do you have a question?
Yeah. Is there a way of, like, say, visualizing X transpose X like top level? Because, like, sure, it makes algebraic sense, but like, without geometric senses in terms of like iterative with respect to a vector.
So X transpose X is the norm of the vector, so that's going to be like the length of it, but then the derivative, yeah, I don't have a good answer for you on that right now. But you can look it up. I can look it up when it comes to my office hour. We can talk about it then. Okay, so now we're going to move on to convexity. First off, does anyone, like, show of hands, who has at least heard the term convex function? Okay, most people, or about half of you, I guess. Does anyone want to provide a definition? Or any intuition? Also, it doesn't have to be formal. Yeah?
It's just like for any 2 points on the function, the midpoint of the line containing these 2 points is always higher than the actual value of that point. The function evaluated at like X version.
Okay, that's kind of it. It's stronger than just the midpoint, though. It's actually every single point on that line. Is it?
For every pair point.
Oh, for every pair point. Okay, in that case, yeah. Okay. Did other people know that definition already, or not? Okay.
Also, the domain has to be like convex.
Yeah, the domain has to be convex, also. Yeah, there are a few different ways you can talk about convexity, like in terms of sets or the functions. All right. Well, maybe if you didn't know the definition, if you saw, well, first if you saw this function, do you know if it's convex or not? See a nod in this graph. Does someone who doesn't know the definition but knows that this is convex want to say why it's convex? Or you don't know that? What is your name?
Aaron.
Eric?
Aaron.
Oh, Aaron? Okay. So someone who doesn't know the definition that Aaron said but still knows that this is convex, do you want to say explain your intuition? Because that's also like another thing to think about for determining things like this. Okay, now. So here's another function. Show of hands, who thinks this function is convex? All right. We have, I saw at least a latecomer thought it was convex. So here, when you see this graph, now do you think that it's convex? No? Okay. So I think you're getting some sort of intuition for the general shape of convex. Yeah?
So the definition you said was basically for any 2 points, the value of the function evaluated at any point between those 2 points is higher. Is that? So what about, like, let's say picking -2 and -1 on that parabola?
Yeah?
So the function evaluated at those 2 points would be less than the left endpoint, right?
So if you were to draw a line between, say, f of -2 and f of -1, it would be like...
Oh, it's higher than that line, I see.
Yeah.
It's not higher than the endpoints. Okay.
Yeah, right. Well, it has to end at the endpoints,
Yeah.
of course, for it to be on there. Yeah, but we'll go through and do some like examples of exactly what this means getting out the definition. So here is the official definition. You have that this function is convex if the function applied to a convex combination of x and y, which is denoted as theta x plus 1 minus theta y, where theta is in this unit interval, or interval between 0 and 1. If it's less than or equal to the same convex combination applied to f of x and f of y. So we talked about convex combinations briefly. So just the definition of convex combination is it's a linear combination of, that has non-negative coefficients that sum to 1. So you've probably already all seen linear combinations where if you have just a set of numbers and just a set of scalars applied to each number and then you sum them up, that's a linear combination. But with a convex combination, you have this constraint that your coefficients, they have to be non-negative, and they have to sum to 1. And you can define a line segment as a convex combination of its endpoints. So here the endpoints are x1 and x2, and if you let theta vary anywhere between 0 and 1, you'll see that you get this line connecting x1 and x2. So when theta is 0, this term gets knocked out, and it just becomes x2. And then at the other extreme, when theta is 1, this expression reduces just to x1. And then as theta varies, you get all the different points along the line. So if theta is 1/2, you get the midpoint of the line, and so on. So to go back to the definition, but now with this understanding of what a convex combination means with respect to a line segment, that means if you choose any 2 points in your function domain, then the function applied to values between those 2 points will never pass above the line segment that connects f of x and f of y. So we're going to go back to the same functions we looked at before, but now we're going to check this definition. So let's focus on our first function. If we picked, what did I put there? I think -4 and 0, and we drew a line, we're good. The line is above the function values in that range. So, working our out so far. Now, let's take the same 2 points on this other function and look at those. So here we have -4 and 0 again. Also working out for that function so far. But now we're going to pick 2 different points. So here, you can see, still doing all right with our parabola. But if we take the same 2 points on this other function, we have a problem because this whole section here is the function is above the line. So it's violating the definition of convexity there. So other than using the definition of convexity, there are a couple other ways that you can determine if a function is convex. So one thing you can do is check the definition, like we did before. But if you know some more information about f, there are other ways that you can look at it. So if f is differentiable, then if this quantity holds, the function is convex. So that's if you have 2 points x and y, the function of y is greater than or equal to the function at x plus the gradient at x times the difference between y and x. And then if you know even more information besides the first derivative, if f is twice differentiable, you have another way of characterizing convex functions, and that's if the Hessian of the function is positive semi-definite. So here, the notation I'm using is this is the same symbol we used for gradient, but we have the square indicating that we did it twice. For the Hessian, sometimes the Hessian is also indicated by like an H, and then I'm sure there are other things maybe varying by field. How many people here have encountered a Hessian before? Okay, most of you. If you haven't, the idea is that here, So suppose your x is an n-dimensional vector. The Hessian is going to be an n by n square matrix, where each element, or maybe I'll just write it down. So suppose you have a function that takes an n-dimensional vector to reals. We already know that the gradient is going to be another n-dimensional vector, where each element, say the ith element of your gradient is the partial derivative of x with respect to the ith component of x. Now, if you were to look at your Hessian, the way that's going to work is, let's see. Can everyone see when I write down this low? Okay, mostly nods. No one said no. So the ijth entry of your Hessian is going to be the second partial derivative of that. First, with respect to the ith element of x, and then with respect to the jth element of x. And then how many people are familiar with the concept of positive semi-definiteness? Okay, one person. Yes. So, positive semi-definite, a matrix is positive semi-definite if for every single vector that you can have, x transpose ax is greater than or equal to 0. So this quantity here is going to be just a real number, right? Because x is going to be an n-dimensional vector. So x transpose is going to be 1 by n, a is n by n, and then x is n by 1. So you just look at the dimensions on the outside. So this is going to be a scalar, and every single scalar is greater than or equal to 0. So like an easy example here is going to be like the identity matrix is going to be positive semi-definite. Because if you have the identity matrix in there, right, it just drops out, then you're looking at x transpose x. And so x transpose x, you're just summing the squares of every single element in your vector. And so if you're summing a whole bunch of squares of real numbers, it's never going to be negative. So we're going to try out the, yeah?
Do you have any sort of intuition for how to determine if the matrix is positive semi-definite? Other than that equation?
Yeah, there are like identities and stuff. That's, in most cases, like you can use this and think about it, but there are some other identities that you can look up. Yeah?
Where does this matrix A come from?
Oh, here I'm just defining A to be or I'm introducing A to give you the definition of positive semi-definite. So here what you would be checking is here this Hessian is going, you can think of that as this is what we actually want to see if it's positive semi-definite or not. So you would just substitute that in, but this is the general definition of positive semi-definite.
How would you determine the second gradient in a particular direction B using the Hessian? So how would you calculate the second derivative in a particular in a generic direction B using the Hessian?
All right, I'm not sure if I understand your question, but do you think would going through an example help?
Yeah, so like I was just sort of relating it back to the gradient. So if you want to find the gradient in a particular direction B, you take the gradient vector and you dot product it with the vector, right? Is that?
Are you talking about like finding a projection or something, or?
No, just
because if you just calculate the gradient, that's going to be an n-dimensional vector. So then if you calculate the Hessian, it's like you're taking the derivative of each element of that vector, but again with respect to your original vector, and that's how you expand to be like n by n.
Okay.
So,
yeah.
Okay, maybe I can start an example, and like if people are getting it, then we don't have to go through the whole thing.
Okay.
But I think other people could probably benefit from an example now that I think about it. Okay, so suppose, yeah, let's just keep our same f from before because it's easy. So we know here that the gradient of f is just going to be x, which again is x1, x2, all the way through xn. So now, if we wanted to take the Hessian of f, we're going to look at each of the partial derivatives here, and then take another partial, but with respect to a different component of x. So we know that it's going to be an n by n matrix. And like this first entry is going to be the second partial derivative of f, and with respect to x1 both times. So here, if we look at this first element of the gradient, and now we want to take the partial, here it's x1, we want to take the partial with respect to x1, what is that? Yeah. Okay, so that one's 1. So in this next entry over here, we're again going to take second of f. So the first time we did it, it was with respect to x1, but now the second time it's going to be with respect to x2. So we're looking at the same element. Everything in this first row, you're going to be looking at the first element of your gradient. So what is the partial derivative of x1 with respect to x2?
0.
Yeah. All right. You probably here. Let's just run a clip for this microphone so it does whatever. Okay. So now let's look at the last, still the first row, but the last column of the Hessian. So second of f, again, the first time it was with respect to x1, now it's going to be with respect to xn. So we're still looking at this one. What is the partial of x1 with respect to xn? 0 again, yeah. So you can see that pretty much every time you're not doing, for this function, every time you're not doing the partial with respect to the same thing you did the first time, it's just going to drop out to 0. And other times it's going to be 1. So for this function, the Hessian is the identity matrix. But if you have more complicated functions, particularly like where you have different products that cross each other, you'll have a more interesting Hessian. Yeah?
So x transpose times the Hessian times x would be the double derivative as we walk along x, right?
What do you mean?
So x transpose a x would give us a number, right? And that number would be how f varies as we walk along x. Like the double derivative along the x direction.
Oh, yeah, I guess so.
Right. So this is just saying that along any direction you just go up. Or like, it's like a generalization of convexity of all directions.
Yeah. So if you think about, yeah, that's a good point. If you think about convexity for just a single variable function, at least when I learned single variable time was like 8-9 years ago, whatever, I was in high school, was you would look, if you wanted to see if a function were convex, you would look at the second derivative, and if it were positive, then you knew that the second, or you knew that your function was convex. If it were negative, you knew that your function was concave. So yeah, this is the higher dimensional analog of that. So we're going to go back to the function that we looked at before. Here it's just one-dimensional. So if we were to look at the definition, which is basically you're looking at all pairs of points to check if the line segment that connects them lies above the function there. You can see that here, this general like bowl shape, that's going to hold. So now, this is a very nice function because we know its first derivative. So here we're going to look at this first order characterization. So we already know that the gradient of f is x. And if we substitute that into our first order characterization there to see if it holds, here I'm just applying the function and also substituting an x for the gradient. And then rearranging, that's just expanding. And then rearranging, so there I moved everything, all the variables over to the left side and multiplied by 2. There you can see that you can factor this. So its factors is a square. And so again, for real numbers, if you square them, regardless of what they are, it's never going to be negative. So this first order characterization holds. And now to look at the second order characterization, which is you check the Hessian. Here, it's only one dimension, so you see that it's one. But here, just now, we generalized the kind of the square function to any number of dimensions, and you see that it's the identity function, which is positive semi-definite, as we discussed. So again, it's convex, which is good that no matter which characterization you use, it says they're all convex. So now the last thing that we're going to talk about is one particular optimization technique. Just introduction to optimization first. So in optimization, you have some function, call it your objective function, and you want to find the optimum value, usually the minimum, but it can also be the maximum. And so you have this function, and you can vary the argument to this function, and you want to find the value where that function achieves its optimum. So sometimes, and this came up when you were like looking for your maximum likelihood estimation or whatever, sometimes you would be looking for like argmax or argmin, something like that. So if it's the argmax or argmin, there, in that case, you want to know the particular value of x that achieves the optimum. But lots of times when you're looking, you only care about the value or the value of the function that is the optimum. But you can use the same techniques to find both. So again, looking for a minimum is equivalent to finding a negative maximum. So here, if you want to minimize this function, if you look at the negative of it, just reflect it about the x-axis, and you can see that if you have, for this particular case, x equals 0 is going to optimize both. So it's going to minimize f of x and maximize negative f of x. So if this is a convex function, then this is a concave function. And for convex functions, the thing about them that is really nice when it comes to optimization is that any local minima are also global minima. So this is very great. So this means that if you found a local minimum, you don't have to continue searching your entire domain because you already know that you found the best solution out of everything. One common optimization technique is gradient descent. As you might guess, it has something to do with the gradient. Oh, who here has heard of gradient descent or used it before? Okay, most people. All right, you're good. You're good. As you already know, and if don't know, you can guess it has something to do with the gradient. So because of that, your function must be differentiable, so you can't calculate the gradient at any point that you might get to. Also, it needs to be convex, so it doesn't get stuck in a local minimum. There are actually lots of times that people will use gradient descent for non-convex functions, but then just do random restarts to see what actually gets the best solution. So maybe it's fine if way off in an area where you're probably not going to be, there's some other local optimum that isn't the one you're really looking for, because if you never get over there, then it's fine. So the fact about the requirement for it to be convex is just so that you're guaranteed to find the global optimum instead of getting stuck in a local optimum. But if you do it enough times, just by chance, you will probably end up hitting a different optimum. You can just look for whatever one is the best. So here, just the formula for gradient descent. You choose a starting point, and then you continue this process until there's no change in what point you're at. So you get an updated value for your optimum, the previous value for your optimum starting at whatever starting point you chose. Usually you choose it at random. You have something called a step size, which is just a scalar. And then you evaluate the gradient of f at your current point, xk minus 1. And you just keep doing this until your xk is close enough to xk minus 1 that you've decided you're not getting any more benefit from completing more steps. So the idea behind gradient descent is that you're kind of stepping down to the minimum value. But how does gradient descent know which way to step? So suppose, here, our favorite function for the evening, and the gradient, which you know very well now. So if you choose this point here, say you want your starting point to be x0 at -4, which direction would you go? To the right? Yeah, because that's the way you get down to the minimum. What about if you started here with x0 +4? Which direction are you going to go? To the left, yeah, to get to the minimum. So you can see that you're taking your step in the direction of the negative gradient. So here, because f of x is x, when you're at -4, your gradient is -4, which would be pushing you this way. But if you go in the direction of the negative gradient, you're going to be heading toward the minimum, and then conversely for x0 at +4, then taking the negative gradient is -4, which will push you in that direction toward the minimum. So yeah, moving in the negative direction of the gradient. So here, this is illustrating the idea on a two-dimensional function. So these circles here are contour lines. Raise your hand if you're familiar with the concept of contour lines and plots. Okay, seems like most people. But just to refresh anyone who didn't raise their hand or was too lazy to, every value that's on the same line takes on the same, so every pair of points on the same line takes on the same value of the function. And here, this was plotted in MATLAB, so the warmer colors mean it's higher, and the cooler colors here, blue, means it's lower. So you can think of this like pretty much literally like a bowl. So you have both x and y dimensions, and then the z-plane is your depth. But we've squashed it down and represented it with contour lines. So you can see that the minimum is here. So in this example, say we started, this was the initial point we took, and then you take a step, and you end up there, take another step, end up there, another step, end up there, and then eventually you end up at the optimum. So here, one thing that you have to consider with gradient descent is you have this step size parameter, which I didn't know, I think it was t a few slides ago. So you have to choose something for that, and that is going to affect the trajectory of your search for the minimum. So if you have a really small step size, you can see here, like I plotted a dot for each time you stepped, but it basically just looks like a solid line because it doesn't get very far each time. I think for this I stopped it after 50 iterations. So you can see that after 50 iterations, it didn't get to the optimum because it was taking very tiny steps at each point. In the middle, this is the same figure as in the previous slide. The step size was 0.3. I think here it was maybe like 10 or so steps to get to the optimum. So at that point, you wouldn't say, go for 50 steps because it would see that it wasn't moving anymore and it would just stop. And then in the far right here, the step size is 0.8. So that's the biggest step size shown here. And you can see that it started off from our initial point and then took a huge step over here because the step size is so large. And then from there, it took a huge step back here, and then it just got stuck in this like ping pong thing, going back and forth between the two. It was taking too big of steps, and it would always overshoot the minimum. So choosing the step size, yeah.
In the second image, it doesn't seem like the steps between points are the same.
Okay. Yeah. So the actual, if we go back to the definition here, you can see that the actual change that you're making is, it's not just the step size, but also the value of the gradient is going to affect it too. So if it's a bigger gradient, like if there's a bigger difference it sees, it's going to take a bigger step in that direction. So yeah, it's not, you're taking the gradient is more than just the direction. It also informs you as to how big your step is. But again, the size of your step can influence the ultimate size of how much you change from moving to x, from an xk minus 1 to xk.
Is there an intuition to how to pick the step size?
Yeah, so there are a few different ways that you can do it. I think in the case when you all will be programming stuff, we will probably just tell you a step size that's going to work, and you can use that. But there are some other smart ways you can do, like line search for choosing exactly which step size is going to be the best for your next step. Another thing that people sometimes do is another thing is you can have a decreasing step size. So if you go back to the, but if you go here, I actually indicated what iteration you were on, so you don't have to keep the same step size at each time point. You can choose it, have it decrease. So some people have it get progressively smaller the more steps you have taken, just because the idea is make a lot of improvement at the beginning, and then when you get closer, it's there's more of a danger of overshooting when you're much closer than you were in the first place. So sometimes people will have a step size 1 over the number, the iteration that you're on. So on the first iteration, and then lots of times scaled by something. So say you have just a t that you're going to have. So your first, your tk at first is t, then on your next step it's t over 2, then it's t over 3. So it gradually gets smaller the farther you go. But there are sometimes fixed works if you can find a good one, but if not, you can do something like line search to find a better one. So I don't think we're going to ask you to do that in this course. So if you're interested, you can read up on it, but it's not going to be required. Here it was again. So another thing that might come up when you're going to be using gradient descent and logistic regression, sometimes it's actually framed slightly differently, exactly the same concept, but for logistic regression, very similar to, so when you were wanted to classify with, say, naive Bayes, when you had a new, or first of all, when you were learning parameters, how did you learn your parameters? There was a quantity that you wanted to optimize. You learned 2 different ways to do it, but in both of them you were maximizing something. Huh?
Was it the theta that you were optimizing?
Well, theta was your optimization variable at that point, but the function, what was the function that you were trying to optimize? Yeah, so for the maximum likelihood estimation, you were trying to maximize the likelihood. So for logistic regression, when you're learning parameters there, you're also going to want to maximize the likelihood. So sometimes, if you keep with that notation of being I want to maximize stuff, then this is actually presented as gradient ascent, where you're climbing up to the maximum. But the only thing that changes there, so to climb up, instead of going in the direction of the negative gradient, you go in the direction of the positive gradient, so this just becomes a plus sign. And then it all goes back to the same concept of if a function is convex, its negative is concave, and so everything applies, but then it's just called gradient ascent. You have to remember to change your minus sign to a plus. But it's all very similar there.
Actually, it's gradient descent, what is the gradient?
So we can go back and look at just the one-dimensional example here. So you can see that the gradient, sorry, were you asking about gradient descent?
Yeah.
Okay, yeah. So here, if you're looking at your gradient, which is just x, at x0, that's going to be -4. So if you move in a negative direction, -4, that's going to send you that way.
Right.
Which is the wrong way.
Okay.
Yeah, so that's why you want to go in the negative direction. And so arguably for a function like this, you don't need gradient descent because you can just like differentiate, set it to 0, and solve and see that the optimum is at x equals 0. But in the case where you can't exactly solve for the optimum of a function, then gradient descent works out really well, which happens to be the case with your objective function for logistic regression. So you'll need to learn that then. Does anyone have more questions about gradient descent or convex functions or derivatives? Okay, so we have some time. I was going to go through an example of comparing MLE estimates to MAP estimates and seeing how the prior influences your final estimate in a few different scenarios. Did someone start to say something? Hearing things. Okay, so here, this is going to be pretty similar to the example that you did in class, but we're going to go through a few different scenarios so you can get a better intuition for how the MLE differs from the map and in different scenarios. So we're going to be looking at a coin flip again. So a coin flip is Bernoulli. So that means that, let's say, our outcome is going to be xi. It's going to be either tails, which we'll denote with a 0, or heads, we'll denote with a 1. And then just the probability that it's 1 is given by theta, the parameters of Bernoulli that we want to learn. So in the, okay. So we're going to look at two different like experiment settings, and then two different priors on theta, and see how that changes our map estimates and also the MLE, if it does. So in our first setting, which I'll call experiment 1, we toss the coin 100 times, and we get 60 heads. And which leaves 40 tails. We're also going to look at putting two different priors on theta. So we already know from lecture that the conjugate prior for a Bernoulli distribution is the beta distribution. So prior 1 is going to be a beta distribution. But here for the parameters, we're going to say 2, 2. And then our second prior, another beta distribution. But it's going to be 200, 200. So to remind everyone of what exactly you're doing in maximum likelihood estimation and map estimation. So for maximum likelihood, does someone want to tell me the quantity that you're trying to maximize? Yeah. So for the MLE, you want to maximize the probability of the data given whatever parameter you have there. And then what about for a map estimate? What do you want to maximize there?
Isn't it just the x given theta times the probability of theta?
Yeah. So here, maximize this product, the posterior of theta given x times your prior. And so you can get at this through Bayes' rule. So with Bayes' rule, you know that this is equal to P of theta given x times P of theta over P of x. But if you're maximizing with respect to theta, this denominator doesn't matter, so you just knock it out. And this is what you put in down here. And so the thing about that Bayesians like is that then you can incorporate this previous belief you have on what the prior is probably going to be. Yeah?
Isn't Bayes' rule probability of x given theta and probability of theta?
So here, Bayes' rule, it's a way that you can flip these two things.
No, so like Bayes' rule is like probability of x using theta is probability of x like given theta times theta. But then that.
So here, this quantity at the top, right? This is if you like reverse the chain rule. This is the joint probability of theta and x.
I think we
Let's
need to
see,
switch the theta and the x and probability of theta and probability of x.
Wait, what are you using?
Yeah, not
The
that.
formula is the other way around. The probability of theta in the numerator and the probability of x in the denominator.
Oh, yeah, sorry. That's right.
And then the same thing for x. The match probability of theta given x. Or probability of x.
Yeah, it should be.
Oh, wait,
probability of
sorry.
x given
Yeah,
theta.
no, sorry, I got all this backwards.
That's
Wait, no, that was right.
I believe this one.
Yeah.
Yeah.
Yeah, so then this one was probability of x given theta times probability of theta.
Yeah, so you look theta as constant, then math will be numerator.
Yeah. Yeah, because originally what you're trying to maximize here is, so originally what you're trying to maximize is the probability of theta given x, which you use, you use Bayes' rule here to get that, and then you know that So originally what you're trying to optimize in your math estimate is the probability of theta given x. You use Bayes' rule, and then you can get at your, it's proportional to, here this is your likelihood, same thing from MLE, times your prior. And so the example that I wanted to go through was using a couple different scenarios and looking at how the prior influences what your estimate is in those cases. So you know from lecture that the formula for your math estimate is, here in this case it's going to be the number of heads plus this beta h minus 1 over number of heads plus your first beta parameter, and then plus your number of tails plus your second beta parameter minus 2. So in the first experiment, what's the maximum likelihood estimator for theta if you got 60 heads and 40 tails?
0.6.
Yeah, 0.6, whatever. And what about with the first prior? like tell me what it is and I'll write it down, and then I already did the numbers, so we know what it is.
Like 60-ish.
It'd be like 60 plus 2 minus 1 over 100 plus 4 minus 2, right?
Right. So that comes out to be 0.598. So here at the same setting, let's look at our second prior. What's that going to end up being?
Place the 2 with 200 and
Yeah.
400.
Yeah. And so that comes out to be about 0.583. So now let's suppose we have another experiment. In this experiment, we only toss the coin 10 times. So, and we get 6 heads and 4 tails. So what is the MLE here? 6 heads, 4 tails. What's the MLE? Huh?
0.6.
Yeah, 0.6 again. But what about the math estimate with our first prior? Yeah. Yeah, so that's 7 over 12, which ends up being about 0.52. And then, what about with our second prior? Alright. I'm assuming you're not answering it because it's basically beneath you at this point. Well, I mean, it's just like the same formula over and over. Like, no, I get it.
I think
So-
you're mixed up the 2 calculations.
Huh?
I think the prior 2 from the first experiment is 0.52 and the other one is 0.583.
Oh, wait, I did my, yeah, sorry. I did my notes and, wait, did I?
7/12 is not 0.52.
Oh, maybe I wrote things down the wrong way. Okay. No. Is it? Alright. Alright, well at this
It
point
doesn't
it's
really
arithmetic.
I
But
was just confused.
okay. Well no, because I thought about like what things meant and like they made sense for the point I wanted to make here. But so you can see here we had one case where you had a lot of data, one case where you didn't have as much data. In both cases, you got the same value for the MLE, right? It was 3/5, 6/10, however you want to say it, in both cases. But then we looked at these 2 different priors. So the priors, in class you talked about how this priors basically incorporating like virtual counts to your example. So here, here you can see that it like is equivalent to adding like this number minus 1 heads, this number minus 1 tail. So here we added like, before you went in, we said, well, let's pretend we already saw 1 head and 1 tail. And here, before we go in, let's pretend we already saw 199 heads and 199 tails. So in both cases, you're sort of biasing your result toward wanting to be 1/2, right? Because you observe equal number of heads and tails in these hallucinated examples. So here, in the case where you had a very small data set, you can see that the values that you got were much closer to 1/2 than when you had this larger data set, because you didn't have very much information that you had gathered beyond the prior to kind of move you away from the prior. And then comparing prior 1 to prior 2, you can see that prior 2 is stronger in terms of like pushing your result toward the prior, just because you had so many more examples that you were looking at. So that's the point that I want to get there. Yeah?
So on the home one we have a beta to 1 prior.
Yeah.
And that corresponds to adding 1 to both the numerator and the denominator, right?
Yeah.
So that means that we're introducing 1 extra example, and it roughly corresponds to adding 1 coin flip, which is heads, right?
Yeah.
So why
So
would
it's
we?
slightly biased in that sense.
it's very biased, right? Like it's too biased
Yeah.
in some sense. So why would we want to do that? Should it be a fraction ideally? Like the number we add to the numerator should be smaller than the number we add to the denominator, right?
Well, so it kind of depends on what exactly you're using it. To be perfectly frank with you, we're using that prior because this was a previous homework problem from another class, and that's the prior that they used. But if you're having trouble with it, if you like want to try something different and see how much that changes your results, then if you want to come and talk with me about that, we can do that. So, yeah, that's the thing with priors. You can choose whatever you want. So sometimes it gets weird. All right, so that's it for today. See you in lecture tomorrow.
Well, that's broken. Yes. Syntax is not that good. Especially in one
Like, I didn't know where this week and I was like, that's gonna be so much fun. I had not time at all. I didn't do work last Thursday, Friday,
Friday, 4 to 5 minutes. Okay. All right.
Oh, I didn't last
Yeah, no, my office hours mentioned that. So far, I've had 2 office hours and a total of 2 people attend.
Yeah, you know, it's the same one, which you know it's the one,
So, in terms of the only thing that we've been recording
One directional
in terms of like getting the content, not as much as a lecture. So I would recommend getting like a lecture to go through the slides. The slides are very, very similar.
You could take one or two.
And some of those previous grades have been recorded and are on YouTube. So, one example,
So we do element by element.
beginning stuff in most of the courses as standard we're not supposed to know. So this is the first time for one but the topics are genius software. So I know for last spring, it was the master's level. Intro ML 601 was like Tom Mitchell and Nina Balkan co-taught it, and they recorded all of their lectures on YouTube. So you can go and I believe they're on the course website. For that, so you can just search 601 spring 2015 and find the lecture. So they'll say just like look for the topics. If you go back and look at the slides, it's suspiciously similar to what was shown in the slides here. So that'll help. Are you all so you have access to Piazza? Are you set up on AutoLab and Q&A? Also, okay. So you have the homeworks where you can get. Okay. Yeah, so go through stuff. If you have questions, there's either an office hour or a recitation every day of the week. But if you can only make it to mine, then just come to mine.
And so there's no like 0 or 1 there.
Yeah, so I think it's relatively early on. There's like no really extra work that you need to catch up on. There is a, it's called Q&A 0. Piazza, you did it? Okay, good. That's just like to make sure everyone has the
2 rows, and the first row is
appropriate background
for
for the course. So if there are things there that you were having trouble with, I would recommend reading up on those.
It's like probably
They're
I given one.
Yeah,
probably
so
only
just
going to
like
get
one
harder
word,
later.
multiply by
When you're learning new stuff on top. But yeah,
and like you
Multiplied
have,
by
sure. What's your name?
Jonathan.
Jonathan. Okay, cool.
Great.
yeah, so that's like the probability.
Sorry, I had a question about
That's like the probability of,
for this assignment.
that's like,
So is it like your accuracy
Yeah.
compared to?
Yeah.
I mean, I don't see how you don't get this.
So we're comparing the output of your code to the output of the correct code, which we have written.
This
So
is-
it doesn't matter,
this is the-
like style doesn't matter. All that matters is you get output, like your output matches ours within some tolerance. And all of our tests are on the same data set that you have.
Oh, so there's no.
So there's no like hidden data set
So
that we're
we
going to
get
test you on that you
unserious.
don't already have.
And we multiply this by that.
And then
we get
everything's like graded as soon as you submit it,
the sum
so
of.
Oh, yes.
there should be no surprises there. Yeah, and you can submit as many
So
times
the
as you want.
words that are in.
Yeah.
that are- Yeah,
Yeah.
so for the words that are in the.
But I mean, for one of them, we're doing funding like that directly, but then there's the other one where it's like.
Probably one.
Yeah, so,
Okay.
yeah, so we do 1 minus this and 1 minus this, right? Yeah.
And so one of them's gonna be
Just the
non-zero.
top and bottom, is like.
What if
No,
you
no, no, but see, okay, these things are gonna exactly line up so
Inside
that,
the word A appears.
like, whether a zero is
Okay.
good
So it
in the
creates
product,
a map estimate of.
there is
one.
gonna be non-zero
Yeah.
to the
And
other
so
product.
then when we have to do like the classifier, when we're trying to check
Like other
what's the
product
probability that the word does not appear.
Like we're adding.
So, okay, if we do element
Yeah.
first,
And
right?
so when we hit zero,
We get a
we're not
vector
quite sure what to do
with
that because
non-zero
we actually
entries in
want
these
log
spots.
zero causes
Yes.
And if we
Okay,
do the
well, log of
complements,
zero is negative
we
infinity,
get a
right?
vector with non-zero
So
entries in
if
these
you've already
spots.
decided that this word has to appear, if it's
So
an
if one
article
of
of
those
that type, when you
probabilities
take the log
is
and that's
zero,
negative infinity,
there's
it just
gonna
means
be
you're never
zero
going to
Yeah, but they
choose
also complement this, right?
that label, right?
Yeah, so.
Which
so
is
then
what
down here,
you would want to do
So.
in the
this is
case
the
that,
thing
like,
corresponding to-
suppose that, I mean, basically what it boils down to
So
is like,
if
if a
A
word does
doesn't
not have,
appear-
or if an article does not have the word A in it, it cannot be an onion article, right? So
In
then
all
when
the
you do
test
this,
data, in all the
like,
training data, yeah.
kind of like a score for it, under the assumption that it is an onion article, and it doesn't have
So
A,
if it doesn't.
it'll end up being negative infinity, which means you're not gonna choose it, but when you think about like conceptually what that means,
Yeah,
it's,
so
you got it
onion
that with
test
saying
gives
like,
us
well, it says
and
the
one
word
minus
A
one
has
plus
to
one
appear in
minus
all
plus
onion
plus
articles,
plus
so then it's like
Right.
sort of like a rule that you can just
What
use in
about-
your head, like, oh, if it doesn't have A, then it
Onion
can't be an
times-
onion article,
onion
which
times-
mathematically is what it comes out to when you take the
No, it's
log of
because-
zero.
It
Yeah,
doesn't appear?
yeah,
Okay,
Yeah.
that would be
Yeah.
Okay,
a,
so that is actually
Yeah.
fine.
but then.
yeah. So there are,
This would be a one.
I remember from before, there was,
But we, like,
I can look into this,
The
but there were some problems
training-
about
the
how
training
exactly
is-
ought
this is
to
one.
This is
handle
different from the training.
negative
Yeah.
infinity.
So
So
it
sometimes
suggests
it would
that
say
it's
like
a
it was
because
not a
like
number,
every onion
which,
copy
in which
site
case,
has an onion.
oh, that's what you've been finding, okay, so there, yeah, I don't remember
Yeah.
exactly, there are some ways that, like, ways that you
Because you're
need to
multiplying this
get at
times
getting
like
this
that, right?
value so
Yeah,
that
so
it comes
this
out
is
as
best
negative
data.
infinity and not a number.
So that's
But I can look into that
No, but it
and
doesn't
get back to
appear
you
in
on
the
that.
training, in the test data.
Yeah, because if it's negative infinity, then that should be fine.
I mean, we only get
There is
this
some-
from the.
yeah.
testing.
No, this is from training.
Sure.
Wait, sorry, this is the thing.
Yeah, and this is the test data. So it doesn't appear in the test data, in the test logs. But it nags everything.
Yeah, so Shindo okay, then what happens with that?
What's that function?
If it really is. So that's where we just have to avoid the math, but negative infinity is fine. Because depending if that's